So it's a great pleasure to have Yao Xiao with us. We'll be telling about equivariant Lagrangian Floer theory on compact toric manifolds.
Okay, thank you for the invitation. So today I'm going to talk about equivariant Lagrangian Floer theory on compact toric manifolds. This is based on part of my PhD thesis at Stony Brook University. Okay, so why would we care about equivariant Lagrangian Floer theory? So first of all, Hamiltonian group actions usually give rise to interesting invariants. So as we know from Noether's theorem, that every continuous symmetry on physical systems give rise to, corresponds to a conservation law. Secondly, we know many symplectic structures arise via symplectic reduction. And Kerwan has a theorem which shows that in some cases, the equivariant cohomology of the symplectic manifold is surjective to the cohomology of the symplectic reduction. And lastly, we might be interested in an equivariant version of homological mirror symmetry. So we'll see maybe hints of this idea in my talk. Okay, so let me talk about the setup. So suppose we have a compact symplectic toric manifold. Of course, by toric, I mean there's a Hamiltonian torus action of half the dimension of the symplectic manifold. And suppose we take also a Tn invariant almost complex structure. Okay, we also consider an associated moment map from X to the dual of the Lie algebra of Tn. And you would have this, by the convexity theorem, you have a convex polytope, which is the image of the moment map. We assume that this moment polytope has m facets, where each facet is given by uvi minus lambda I greater or equal to 0, and vi is the inner normal of the facet representing the ith facet. Okay, the actions I'll consider are subtori of the original Tn. So we assume the dimension of G is R. And the Lagrangian submanifolds we'll consider are the Lagrangian torus fibers of the moment polytope of the interior points in the polytope. Okay, so we'll take coefficients in the universal Novikov ring to define our Lagrangian Floer cohomology. Here, I think most people know the definition of this ring. It consists of a series of this form where AIs are complex numbers and T is a formal variable which keeps track of the energy, and E is a variable which keeps track of the Maslov index. And we assume this the series converges in the t-adic topology. And we also use, so yeah, and we have this, this is the universal Novikov ring, which has this formal variable E, and the universal Novikov field is the fractional field of this universal Novikov ring. And we might also use the Novikov ring without the variable E and its fractional field. So we drop the word universal in this case. Okay, so let's discuss the definition of the equivariant Floer cohomology. So as we said, we consider the TR equivariant Lagrangian Floer cohomology of a Lagrangian, which is a torus fiber of the Tn moment map, Tn moment polytope, and with coefficients in the universal Novikov ring. And here we need some extra data where B is a first cohomology class of the torus fiber with coefficients in the Novikov ring. The idea is, of course, by considering an equivariant A infinity algebra given by the Cartan model of the G action on L. So let me remind you what is a Cartan complex. So the Cartan complex for the G manifold L is given by the G invariant differential forms, G equivariant differential forms, where by that I mean the G invariant elements of the tensor product between the RAM complex of L and the symmetric algebra on the dual of the Lie algebra. Remember here, G is the subtorus TR. We can define a G equivariant infinity algebra where the complex is given by the Cartan complex, and the equivariant infinity operators are given by counting disks equivariantly. Okay, and we can define an equivariant Floer cohomology because the M1 operator, M1GB, satisfies that M1GB squares to 0. If you compose it with itself, it becomes 0. So I can define the cohomology to be the cohomology of the Cartan model with respect to this M1. Okay, a key point here is that the M0GB is a multiple of the unit of the infinity algebra. In particular, this multiple is given by this constant in front of the, so here E is again the formal variable for keeping track of the Maslov index, and this is the potential function on this pair L and B. So potential function is a.
So e to the power of 1 with equal Maslov 2, right?
Yes. In the case of toric manifolds, yeah, only Maslov 2 contributes. So yeah, we consider compact toric manifolds if I didn't mention it. Yeah. Okay. So the potential function seems to be messy because the domain is like a union of set of this form. However, we can use an embedding of this from this set to lambda star to the n. Here, lambda star means lambda minus 0, such that potential function becomes a Laurent series from lambda star to the n to lambda. So here, this I is embedding where I take, so u1 after un are the coordinates in the moment polytope. So u1, ui's are in T star. So like if you identify T star with Rn, ui's are u1 after un is an element in Rn, and B is B is the first cohomology class. It's a first cohomology class on mu inverse of U, and it's of this form. So I embed u1, I embed ub this way. So yi is e to the xi t to the ui. So this way, my potential function will become a Laurent series. Okay, so later I will show a result which tells me what kind of Lagrangians will have a non-zero equivariant Floer cohomology. And with this tropicalization map, I could see those Lagrangians and manifolds through inside the moment polytope. So the tropicalization map is just the coordinate-wise valuation map. So the valuation map is defined to be, so valuation of a series of this form is the minimum of the energy, such that AI is non-zero. Okay, so as promised, I have a result which tells me what kind of Lagrangians and manifolds have non-zero equivariant Floer cohomology. So this holds if and only if if I consider this embedding sending ub to y, where y is, remember, an element in lambda star to the n, this LUB has non-zero equivariant Floer cohomology if and only if the gradient of potential function vanishes on the normal directions of the G action. And of course, I would only want to consider objects that I consider, right? So I need the Lagrangians to be torus fibers of the interior of the polytope. So I need to intersect the solutions with trop inverse of interior of the polytope. Okay, and the idea of the proof follows from that I have a spectral sequence which whose E2 term is the equivariant de Rham cohomology of the Lagrangian, and it converges to the equivariant Floer cohomology of the Lagrangian. And this spectral sequence collapses at E2 page if and only if M1GB vanishes on equivariant equivariant de Rham cohomology of the Lagrangian itself. And also here, I use the fact that the partial derivative of the potential function in some direction is equal to M1G in that direction. So, okay, next I show that the critical point, so this set of Lagrangians with bounding cochain data is that have non-zero equivariant cohomology, Floer cohomology. This set I mentioned in theorem 2 is a rigid analytic space. And I proved that when the symplectic manifold, the compact Toric manifold, is CPN, or if it has complex dimensions less than or equal to 2, then we have a dimension result, which says the dimension of this rigid space is equal to the dimension of the torus. In particular, as promised, this would allow us to locate the Lagrangian torus fibers with non-trivial equivariant Lagrangian Floer cohomology by tropicalizing this rigid space. Okay, next I have a non-displaceability result. So any Lagrangian torus fiber which appear in the previous mentioned set with G delta would be non-displaceable by equivariant Hamiltonian diffeomorphisms. Okay, so let's look at some examples. So consider CP2 with the moment polytope, which is a right triangle, isosceles right triangle, whose facets are given by the alpha inequalities U1 greater or equal to 0, U2 greater or equal to 0, and 1 minus U1 minus U2 greater or equal to 0. And FOO have proved that the potential function of such a compact toric Fano manifold can be determined by the moment polytope, the facets of the moment polytope. In particular, in this case, the potential function would be given by y1 plus y2 plus t over y1 times y2, where this potential function, we consider it as a Laurent polynomial from lambda star squared to lambda. Okay, we can consider the subtorus action by the sub S1, where S1 embeds into T2 in the following form. So T is mapped to K1T, K2T, where of course, we don't want to consider trivial subtorus in this case. So K1, K2 are not both 0. And the condition for the Lagrangian Floer cohomology to be non-zero would be the vanishing of this partial derivative of the potential function in the normal direction. So this means that I need negative K2y1 plus K1y2 plus K2 minus K1t over y1y2 to be 0. Okay, so there are a few cases. So the first case would be all of the coefficients here are non-zero. Then the corresponding, so the corresponding rigid analytic space is given by if you take the, so if I fill these points, these 3 points, then I will get an affinoid space given by the maximal spectrum of lambda y1, y2, z over, this is the first, the derivative of the, this is the, this f I'm considering, and y1, y2, z minus t. So the rigid analytic space is W minus copy inverse of the 3 vertices. And as expected, this original, so if you remember FOO's result about compact Toric manifolds, this barycenter was in a similar space, and it stays in the equivariant case. So we also have the case where, so there are two cases which are similar. One is K1 equals 0 and K2 is non-zero, which means that I embed S1 into T2 using the second S1. The rigid space in this case would be given by the vanishing set of, again, this original F I have here intersecting with trop inverse of the interior of the polytope. And if you compute this, you'll get a rigid annulus. And similarly, I have it for K1 non-zero and K2 equals 0. So the pictures you get, so these are the Lagrangian torus, Lagrangian tori, which have non-zero equivariant Floer cohomology. And similarly, I have it when K2 equals 0 and K1 is non-zero. So these are the pictures. So yeah, so we see these Lagrangian tori with non-trivial equivariant Floer cohomology in the pictures. And another case I can consider is the trivial subtorus action. So here I embed only the trivial, the identity element to T2. Then I have to consider, because because I need to consider the vanishing of the gradient of the potential in the in H identity L, which is the full HL. So I need to consider these both partial derivatives. So this is similar to what happens in FOO. I need y1 minus t over y1 y2 to vanish, and also I need y2 minus t over y1 y2 to vanish. Okay, then this rigid space, which contains all the Lagrangians with bounding cochain data, which has non-trivial equivariant Floer cohomology, would be identified with this the intersection of this affinoid space with trop inverse of interior of delta. So this space is again lambda y1 y2 z over the two Laurent polynomials I consider, and there's a relation between the three variables here. So the three variables each represents a facet of the polytope. And in particular, if you want to see this, if you want to locate this set in the polytope, you get 1 over 3, 1 over 3, which is the barycenter of the polytope. And one might know from previous work of FOO that this is a generator of the ordinary Fukaya category. So this recovers the ordinary Lagrangian Floer theory. Okay. Another example. How much time do I have?
1 minute.
Okay. Yeah. Okay. So maybe I'll just I wouldn't talk about the details of this example. So if you do similar things for this product of two spheres, then you would see pictures like this, where this corresponds to you embed S1 with both K1, K2 to be non-zero, like this. And these points in the polytope correspond to the Lagrangian torus fibers with non-trivial Floer cohomology. And similarly, if you embed it in other ways, then you get these pictures. And the rigid space here would be would be a unit. So here is a unit. So this rigid space correspond to this case would be a union of two analytic annuli, and similar here. And again, if you consider the trivial subtorus action, you recover what happens in the ordinary Lagrangian Floer theory. And the picture you get is this, again, is the barycenter. And this generates the ordinary Fukaya category. Okay, thank you very much for your attention.
Thank you. Let's thank Yao. Very good. Any quick questions for Yao? Any quick questions?
Is there a general argument that says that the barycenter is somehow plays a special role in the usual Fokai category?
The barycenter, yeah, I think it's a result maybe of Evans Lakili. Yeah, I don't have the reference now, but if you search, I think you for compact toric funnel at least, it's a result of Evans Lakili, and I think
and it seems that you're always able to locate it, like this, just by intersecting critical levels.
Yeah.
Very nice. Thank you.